Hey guys, here we go. Topic 4, activity and half-life. So up to this point we've been talking about the types of radiation. Now we're going to look at the time evolution. What if you have a population of unstable nuclei, how does that population decrease in time? Okay, so let's look at that first. So we're going to let n naught be the number of unstable nuclei at t equals 0, whenever that is on somebody's clock. And then at a later time, we'll talk about n of t, the population of unstable nuclei at that later time t. So these are both just numbers. Now what we find out is, and this is an important observation, the rate of decrease in the population is proportional to the population. So in other words, when you start out with a big population, the rate of decrease is rather high. But as the population decreases and the number in that population gets smaller and smaller, the rate of decrease also gets smaller and smaller. So it is not a constant rate. The rate decreases in time. Now the fact that it's a straight proportionality, we can write that as dn dt is proportional to minus n being the population at time t. I need that minus sign there because I know since the population is decreasing, mathematically, that rate, that dn dt is going to be negative. So how do I make that an equation? I need a proportionality constant. And in a stroke of brilliance, right, somebody decided let's use lambda for that proportionality constant. Okay, so in this topic, right, in this subject of nuclear physics, at least here in this connotation, lambda is not wavelength, it's what we call the decay constant. Okay, so how do I solve that differential equation? You guys have had diff EQ, I'm sure you covered this one. That's going to be an exponential function. So the solution, and you can check it by taking the derivative, the solution is n at some time t is the initial n naught times e to the minus lambda t. And again, lambda we call the decay constant, which is going to have SI units of inverse seconds. But any units of inverse time will be fine. And so each isotope, each radioactive unstable isotope has its own decay constant. The next thing, here's just a picture of what that exponential decay is going to look like. And mathematically, if you think about it, right, if I look at slopes of tangent lines, lines tangent to this green curve, that's going to be the dn dt. So you can see how the slope, right, it's always negative, but it's getting closer and closer to 0. So it's not a constant rate of decay. Okay, so let's now relate lambda, the decay constant, to what we define to be the half-life. So the half-life, and we're going to use capital T subscript 1/2. This is the average time it takes for the population to reduce by 1/2. All right, that's it. Simple definition. And again, it's an average time, emphasizing the fact that, let's say I prepare 100 samples of a certain isotope, and initially all those 100 samples have the same population. If I look one half-life later, not all 100 are going to have exactly 50% or half of the population. There's going to be some variation. So this is the average time. Okay, so if we take that definition, I have a note here to look at the isotope data. Yeah, so if you go to the isotope data sheet, you'll see in the last column, I'll show you guys, you're going to get the half-life of the isotope. So again, if I click right here on our course page, you can see this last column is the half-life if it's a radioactive isotope. And these half-lives are all over the place. There are certain isotopes that have extremely short half-lives and some that have really long. For instance, if you look at tritium. Tritium is a common name for a hydrogen-3. It has a half-life of 12.33 years. Okay, here's a ridiculously short half-time of 10 to the minus 17 seconds, about 7 times 10 to the minus 17. That's that weird isotope of beryllium-8. If you think about beryllium-8, it's 4 protons and 4 neutrons bound together. So what happens is, if you fabricate some beryllium-8, almost immediately it's going to split into 2 alpha particles, 2 protons, 2 neutrons, okay? But you'll see half-lives all over the place. Some of the bigger isotopes, like your lead isotopes, have really long half-lives. Look at lead-204. Its half-life is 1.4 times 10 to the 17 years. I mean, that's greater than the age of the Earth, much greater than the age of the Earth, right? We've been around our solar system for about 5 billion years or so. Okay, so it's really metastable, but it is radioactive, but the decay is going to be extremely long decay, a really long half-life. Anyway, you can look at half-lives in that table if you want. Okay, let's get back to our presentation. So what we're going to do next is we're going to relate the half-life to the decay constant. Okay, so by definition, the population 1 half-life later has to be the initial population and not divided by 2. So I'm going to stick in, all right, if I take my exponential function, I'm going to stick in little t is equal to half-life. So by definition, n of t has to be half of the initial. The initial population is going to divide out. So now I can solve this for my half-life. Okay. Now, if I do that, right, I'm going to have to take the natural log of both sides because I want to get at the exponent. So if I take the natural log of 1/2, I'll get my exponent of minus lambda times half-life. Then what I do is I switch the sides. I multiply by -1. I make use of the fact, right, that I can bring that -1 into the exponent with my exponent rule for logs. So the log of 1/2 to the -1 is the same as minus log 1/2. But what I'm going to do right here is I'm going to say, wait, 1/2 to the -1 is just 2. So I'm going to convert that negative log 1/2 to log of 2. So I end up then with the half-life as log 2 over the decay constant lambda. And log 2 is about 0.693 if you want an engineering equation. All right, so we'll use this a lot to get decay constant from half-life or vice versa. Okay, now let's define the activity. So the activity is the rate of decay. And I'm going to use the symbol R of T. Some sources will use A for activity, but I'm going to use R for the rate of decay, also known as the activity. So I can relate that to the population by saying it's the time derivative of the population. I am going to multiply by -1 though, because I want my activity to always be expressed as a positive number. And I know that the n dt is going to be negative since the population is decreasing. Okay, so what I can do next is I can stick in my exponential function for big N, right there. I take the derivative of that. That's going to pull down, what, a minus lambda, right, from this exponent, but I multiply by my -1 here. So I'm left with lambda times the constant n naught e to the minus lambda t. But if you notice, right, n naught e to the minus lambda t, well, that's the population function n of t. So I'm going to get a very important relationship. The activity at any time is the decay constant times the population at that time. So if t equals 0, r naught is lambda n naught. If t is some other time, I can find the activity at that time by taking lambda times the population at that time. And then if I stick in the exponential function for n, I'm going to get r equals lambda n naught e to the minus lambda t. I'm just going to call lambda times n naught r naught, the initial activity. So I get that this exponential function, the activity at some time t, is the initial activity times e to the minus lambda t. The units, again, are going to be number of decays per time. All right, so I want to make an important distinction. Activity has units of number of decays per time. Lambda has units of just inverse time. Okay, so don't give lambda units of decay per time. It's inverse time. You'll see that when we do an example in just a sec. Just want to make a note that you get the same exponential decay with the activity as you do with the population. Okay, so it's the same exponential dependence on t. Okay, let's talk about units of activity. SI units are decays per second. That's given a special name of becquerels, or uppercase BQ. So if I say 10,000 decays per second, that's the same as saying 10,000 becquerels. There is another very common unit that's used called the Curie, named after Marie Curie. It's actually a big unit of activity because it turns out Marie was, and her husband, I think it was Pierre, they were dealing with humongous amounts of radioactive isotopes when they were doing their measurements. So they were getting really big activities, which actually did end up killing Marie. And Pierre also, well, he actually got hit by a horse and carriage. It was a terrible way to die, but they think he was probably suffering from radiation sickness when it happened. Anyway, here's a conversion factor that you should just write down, and you'll use it. 1 Curie is 3.7 times 10 to the 10 becquerels. Okay, so if that's at the bottom of your screen in this video, just look at the PowerPoint. You'll see it. Okay, so the Curie is actually a really big unit of decay, but we still use it. It's sort of ironic, though, because for typical activities, you might have nano Curie and micro Curie because the Curie is such a big unit of activity. But it is common, so know both. Okay, let's do an example. How many years will it take a sample of plutonium-239 to reduce its activity by a factor of 50? Here's a typical question you should be able to answer. Now, the first thing I have to do is I got to find information about plutonium-239. So I need its half-life. If I go to that table, I will find the half-life is 24,100 years. Okay, if you go to that isotope data table, you can find it. If you don't trust me, I shouldn't say that. I just want to show you where that is. So if I go down to plutonium, right, that's going to be atomic number 94. Here's plutonium-239. It's the only isotope that's listed in this table. There are more isotopes. But if you go to the last column, there's that 2.41 times 10 to the 4 years. Okay, so that's where I got that half-life. So then what I'm going to do is once I have the half-life, I'm going to find the decay constant. Now, because I'm putting in years, right, for half-life, my decay constant is going to be inverse years. Okay, so then what I'll do is I'll get my time-dependent function for the activity, and I want to know how long does it take for the activity to reduce by a factor of 50. So I want my R of t to be my initial activity over 50. You notice the activity, right, the initial activity R naught's going to cancel, so it doesn't matter what it is. Right? I need my exponential function e to the minus lambda t to be 1 over 50. So then I take natural log of both sides, right? Because I'm after something in my exponent. I solve this for t. I use the fact that negative 1 log of 1 over 50 is the log of 50. But in your calculator, you can just punch in negative 1 times log of 1 over 50. Right? Divide by lambda. Since my lambda is inverse years, I'm going to get years out. So it's going to take about 136,000 years for that activity of plutonium-239 to reduce by a factor of 50. Okay? So know how to do a calculation like that. Here's another one you should know how to do. What about if I give you a population and I want to know an activity? All right, so suppose cobalt-60 sample has 3 times 10 to the 12, 3 trillion atoms. What's its activity? Well, here I'm going to, again, have to find out what the half-life is of my isotope. I'm not going to show you this on the video, but if you go to the isotope data table, you'll find out it's 5.271 years. I think, if I remember, cobalt has an atomic number of 27. So I find out what my lambda is, 0.13147 inverse years. Now I'm going to use this relationship. The activity is always related to the population through the factor of the decay constant. So R is always lambda n. So I'm just going to put in my lambda and my n of 3 times 10 to the 12, and I get this many decays per year. I'm getting years because my lambda is in inverse years. Now, if I want that in, let's say, becquerel or Curie, I'm going to convert my year to seconds. And that's what you see me doing here. So all I'm doing is I'm multiplying by conversion factors, remembering that my year is downstairs in the denominator, to change this to 12,498 decays per second, which is 12,498 becquerels. And then I'll multiply by my conversion factor to get 3.4 times 10 to the minus 7 curies, or I could express that as 0.34 microcuries. Okay? All right, one other thing I want to discuss, this is a neat thing to consider. It's the probability that a certain nucleus is going to decay in a certain unit of time. All right, so you're going to need to know how to do this for one of the computer assignments. So let's see if we can figure this out. Let's let P of t be the probability that a nucleus will decay in the next unit of time, whatever that is, 1 second, 1 week, 1 year. So therefore, 1 minus that probability is the probability that a nucleus will not decay in that next unit of time, right? So that means if I want to know what my population of unstable nuclei is at some time t, I'm going to multiply by initial population by the probability that a nucleus will not decay, which is 1 minus p, right? So now if I stick in my exponential function for my population, I can solve this for that probability. There you see it right there in the red rectangle. So the probability that a nucleus will not decay in the next unit of time is 1 minus e to the minus lambda t. Let's use this for an example. Let's go back to that cobalt-60 sample. What's the probability that one of the nuclei in that sample will decay in the next week, year, or 10 years? Okay? All right, so remember, I've already found out what my half-life is and my decay constant in inverse years. Now, because I do have a time unit of a week, it's handy to figure out what lambda is in inverse weeks. Or I guess I could convert my week to a year, right? Whichever way you want to do it. What I did is I found out what lambda is in inverse weeks, right? By multiplying by the conversion factor. 1 year is about 52 weeks. Okay, so that'll be close enough. So now I can use this equation for my different time units. So my first one is 1 week. I put in 1 week for little t. I put in my lambda in inverse weeks. I get 0.0025, which is 0.25%. Okay, so not a big percentage, but that's expected because the half-life is over 5 years. So the probability that a nucleus will decay in the next week should be really low. What about if that's 1 year? Oh, okay, that should be a little bit larger, right? And if you actually put in 1 year and lambda in inverse years, you get 12.32%. What about 10 years? Well, that should be much larger because that's almost 2 half-lives later, right? And in fact, it turns out to be 73%. So know how to do this type of calculation also. All right, bye-bye.